And so the mass of this thing is 360 kilograms, okay? And your mass. And when it hits the atmosphere of Mars, which is 128 kilometers, this thing is going to be going about 5.5 kilometers per second. Okay, so to give you some perspective, that's 5,500 meters per second, which is about 3 miles per second. So that's like going, if you're up at 53rd and Maze Road, you're going to 45th, and then 39th and 27th. So you're going from 53rd to 29th in 1 second. Okay, so that's how fast this thing is going. So obviously it carries a tremendous amount of kinetic energy. Now, I know you all have had 9 days off and slept a lot and played God knows how many stupid video games. But
Hey, don't talk like that about Red Dead Redemption. Yeah. You should play Red Dead Redemption.
oh God, no.
It's a
Yes, you
Western
should.
game.
It's all right, man. It's all right.
Okay, so quick refresher. How do you calculate translational kinetic energy? Not one half. Kudos on that one, Vonda. Yeah, you're solid on the 1/2, girl.
MV squared?
MV squared, okay. Right?
Felt like I'm looking at a cheat sheet.
So, let's figure out just exactly how much kinetic energy this thing has, okay? So, the mass is 360 kilograms. That's like a small car, okay? So I was actually out there when they were building it at the Jet Propulsion Lab. Jet Propulsion Lab basically it does the dirty work for NASA, but NASA doesn't want to do. So they basically says, hey, we need a Mars probe built. They give the job to JPL and they build it. So we got 360 kilograms. It's traveling at 5.5 kilometers per second, which should be about 5,500 meters per second. Okay. Squared. So somebody run the numbers. Take 1/2 times 360, otherwise known as 180, times 5,500 squared.
Great. You using the fancy iPad?
Are you using the iPad?
I'm being efficient.
Okay.
Yeah.
So how about that answer, though?
Was I supposed to calculate that?
Yeah. Great, Brink. You're like the designated
Oh, okay,
calculator,
okay.
man.
All right. Oh, your head's in the way, bird camp.
Oh, God. Sound like my gallbladder.
That's what he's gonna get.
5.45 times 10 to the 9.
There she blows.
5.45 times 10 to the 9th.
I don't like that one.
Now, what units?
Joules?
Joules? Okay, right. Now, that's the energy that it has because it's moving. That's a really, really big number. Now, what other type of energy does it have?
Potential.
It has up because at the point of interface with the atmosphere, and this is going to be a key component of this story. The atmosphere of Mars is only about 1% as thick as our atmosphere. So imagine that our atmosphere was like decreased by 99%. Basically, it would to a certain extent be almost like a vacuum. Okay? So this is why everybody says, oh, we'll colonize Mars. Okay, you're colonizing a planet that's a vacuum. Okay? Good luck with that. So anyway, but it's 128 kilometers above the surface. This is when it's going to hit the atmosphere. Okay? It's going to be going 5.5 kilometers per second and 128 kilometers above. So what do you need to calculate gravitational potential energy? You need 3 things.
You need G.
Equals mg
And the height.
height, right? Okay? It's a function how high it is. So let's figure out gravitational potential energy. So we got the mass, which was 360 kilograms. Now, are we going to use 9.8 meters per second squared for G?
No.
No, we're going to use G on the moon or on Mars, which is about 3.6 meters per second squared. And then we have a height of 128 kilometers. We're going to leave that in kilometers. No, change that in meters by multiplying by 1,000. So I got 128,000 meters. So somebody take 360 times 3.6 times 128,000.
1.66.
2.9 8 times 10
What?
to 10.
Wait, we have 360 times 3.6 times 128,000.
I put 360 twice, I don't know why.
Okay, I have 1.66 times 10 to the 8th.
Times 10 to the 8th joules. So that's how much gravitational potential energy. So in other words, if you had just stopped this thing and held it 128 kilometers above the surface of Mars, that's how much UG it would have. So how do you think we're going to figure out the total amount of energy that it possesses? Add those two numbers together. So Mad Max, take that and add that to 5.45 times 10 to the 9.
5.61 times 10 to the 9th.
Okay? Now, here's the problem. That's a huge amount of energy. So, if you want to safely land this thing, do you want it to have a lot of energy or just a little bit of energy when it lands? Just a little bit, okay? Big impact lead, or big kinetic energies lead to big impact craters, okay? And you've just wasted millions upon millions of dollars, and everything else is just gone. So you've got to figure a way to get rid of that energy. So basically, you have two different methods. And it's a nice comparison about what happens when you re-enter the Earth's atmosphere versus what happens when you enter Mars. So Mars has an atmosphere. This is why they have dust storms, okay? Not much, right? You don't have rain or anything like that. They think it might have had an atmosphere later on, which is why you've got like, it appears to be like riverbeds. So they'll actually deploy a parachute, okay? So the parachute is, what's the function of the parachute? Slow down. To reduce the velocity, to reduce the kinetic energy. So this is like how many joules of energy you have to get rid of, okay? This energy has to go somewhere. The energy has to be conserved. This is the energy that you're going to have in the system. It's got to go somewhere. So you deploy the parachute. That's going to slow it down a little bit. So basically, anytime you have a parachute or anything moving through an atmosphere, that's creating drag. It's creating thermal energy. So we're going to lose some of that thermal energy to deploying the hypersonic parachute. Not much, but a little bit. But you still got to get rid of all this energy. So then they're basically going to fire a series of thrusters and that are going to slow this thing down. So guess what? If you know how much energy you have to get rid of, you know how much energy that those thrusters have to provide to slow this thing down. Because that energy has to be conserved. It has to go somewhere. And so basically, when you look at this calculation, if you're the engineer, you've got to say, okay, we've got to find some way to get rid of this. Now, if you look at what happens on the Apollo missions and returning to Earth, or the space shuttle, or anything where it's our atmosphere, we've got a relatively thick atmosphere. And so what that means is that we can, because we have such a thick atmosphere, we can transfer a lot of that kinetic energy into thermal energy, which is why you have heat shields. Okay? So the heat shields basically take that kinetic energy of motion of the spaceship and transfer all of that into thermal energy. And it heats up the bottom of the ship and it begins to burn off. Okay? And that's where we lose a lot of it. So when you look at even like the Apollo missions, you know, they were kind of all the way back to the moon, they were hauling the mail when they hit our atmosphere. We still had the parachutes, but so much of that energy was lost in the thermal process. We can't do that on Mars because it has such a thin atmosphere. So that's why they have to have a separate set of engines, rocket engines that will fire in the opposite direction of motion to slow this thing down. Now here's the bad thing, and they call it, and the entry procedure is called 7 minutes of terror. That's what they refer to it as. Now so if you when you see this, the reason it's called 7 minutes of terror is that's kind of when it hits the atmosphere until it actually lands. But here's the problem. If you're trying to land an airplane, you have like a real-time option in terms of what's happening. You're seeing the landing, you get a feel for what the wings are doing, you have all that. Well, because this is all being transmitted, the sensors are transmitting this information back to Jet Propulsion Lab in Pasadena, California, that's about a 4-minute time delay. even traveling at the speed of light. So basically, if by the time, let's say, for example, there's a problem on re-entry, the parachute doesn't deploy. Okay, it sends that signal back to us. That takes 4 minutes. Well, by the time we get the signal and we go, oh, crap, this is bad. And then you hit like, okay, back up, hit the reserve deployment chute. Well, that's another 4 minutes to get that signal to get back. Guess what? Where's the Mars lander by the time it gets back to there?
Stuck in an ocean.
Yeah, it's buried in the Mars surface at this point, okay? So that's why it's so difficult, because we can't get a real-time display in terms of what's taking place, because you have such a time delay between when that signal is sent and when we get it. So basically, when you're writing the program and you're planning for these contingencies, you basically have to build in the program, okay, how is this thing going to be able to fix itself? Because we can't. Because by the time we get there, and it's going to be cool if you get a chance to see the highlights of it. So you're going to see, hopefully, the people being very excited and, oh, we did it. It's like, well, you're going to find this out after it's either landed or crashed, because there's nothing you can do about it at that point. So the other thing that you see, and I saw this when I was out visiting Michael, even though they're horribly, these are the most intelligent, scientifically minded group of people that you'll ever see, otherwise known as nerds. But they have one solid tradition. They're going to have jars of peanuts in the control room. Okay, like Planters peanuts. You'll see jars of these Planters peanuts. And they're very superstitious, because what happened, this was in like probably the early 80s. When they started, they had this tradition, and no one really knows how it started, of eating peanuts during the critical phases of the landing or the launch. Okay, that was the tradition. And so for whatever reason, they stopped doing that. And then they started having all these epic failures. Okay, like the most famous one was one they sent to Mars. And they figured out like half of the computer language was written in the metric system and half the language was written in the English system. And so one guy said 32, and one group thought that was 32 meters, and another group thought that was 32 feet. And so when they merged the two codes together, they didn't realize that until they figured out why it crashed and burned, and they went back and they said, oh, we feel like schmucks. And so basically GPL had all these epic failures. And basically NASA went to them and said, you either get your stuff together and you get us a successful landing, and we're going to find somebody else to do this, because we're tired of wasting millions upon millions of dollars on very public epic failures. So they said, okay. So they thought, okay, what did we used to do? And one guy said, we always used to eat peanuts during the critical phases of a launch or a landing. Okay, we're gonna go back to that. And so, no, it's a true story. And so now you have these jars of, when you look in the control room, JPL, you're going to see jars of peanuts around the room, because everybody's got to eat some peanuts, because it's good luck. Even though, scientifically, there's absolutely no basis whatsoever in terms of the cause and effect of someone sitting in a control room in Pasadena, California, and how that's going to impact what's happening on a probe that's traveling at 5,500 meters per second trying to land on the surface of Mars. But yet that's the tradition. And so I asked him, I said, because he's up at the Cosmosphere now for the landing. And I said, did you bring peanuts? He goes, oh yeah, I brought 3 or 4 jars with me, even up here, just for good luck. So if you ever see that, and you ever see the jars of peanuts, that's why they're doing that. So anyway, so it's kind of a cool deal. So if you get a chance, Thursday during Encore, I'll remind y'all, but it's a cool deal. It's a good story. Okay, got that idea. All right.
Yeah.
Okay. Okay, McGriddle?
Yeah.
Okay. All right. So speaking of conservation of energy, let's say that I have because I'm missing a gallbladder and I've got 5, things across my stomach. I used to use the the bowling ball. We're just going to use the golf ball today. So here's go to the golf ball, and he's got a mass of 0.1 kilograms, right? And Gary is 2 meters above the ground, and I'm going to drop Gary, and he's going to hit the ground. So here, boink, okay? So I want to look at this whole thing from an energy perspective. So all we're going to do is basically find a new way to analyze this situation, strictly from an energy perspective. Now, here's the deal. Energy has to be conserved. Whether you're talking about dropping Gary the golf ball, or if you're talking about landing the InSight probe on Mars, okay? That energy always has to go somewhere. So if you know how much total energy that you have to have, then that's the amount of energy that has to be in the system. So the same thing is true if you look at the InSight lander. Okay, it was launched, I think, like March 25th from Vandenberg Air Force Base in California. So they had to know, okay, well, how much energy is that going to take? Okay, well, we got to get it, into orbit around the Earth. Okay, and then we got to fire the engines. Okay, well, that's going to take a certain amount of energy. And then we're going to go to Mars, and then we got to slow this thing down by firing the engines there. So they said, okay, we're going to need a lot of energy. Now, so in the case of a rocket, where is that energy stored?
Fuel.
Thrusters.
Well, not in thrusters, but that's how it's used. But where's the energy itself stored?
Fuel.
In the fuel itself. She said, okay, if we need 10 to the 9th joules of energy, and we know each chemical reaction produces X amount of energy per joule, per reaction, well, how many reactions are we going to have to make that deal happen? Because that amount of energy has to remain a constant. So it's the same idea. So we're just going to use that same idea, we're just going to use it on a much smaller scale. So let's start at the beginning. So let's say that Gary's on the ground, and I lift him up to a height of 2 meters. When I do that, do I do work? Agree? So I'm going to take Gary who's on the floor, and I'm going to lift him up to a height of 2 meters. Do I do work?
Yes.
Why?
Is the force is moving in the direction of what the golf ball is?
Yeah, I'm exerting a force over distance, right? I'm lifting this thing up, and what type of energy am I storing? Potential. So what's the simplest way to calculate work?
Force times distance.
Force times distance, right? So how much force did I have to exert? Olivia, I got a 0.1 kilogram mass. How much force did I have to exert to lift Gary up? On Earth, not Mars. Let's clarify that.
9.8 times the mass,
And which gets me,
which is
what'd you say? Oh, you were right.
0.98.
Yeah.
Yeah.
So the force that I have to exert is 0.98 newtons. Okay? Just gonna go lift it up. Here we go. We're off, right? So that's 0.98 newtons. Okay, that's kind of cool. So I'm going to lift this thing straight up. So work is force times distance. So I got 0.98 newtons. I'm going to lift it up to a height of 2 meters. And oddly enough, I'm going to get 1.96 joules. Okay? Now, the other thing that you can look at in a situation like this is, oddly enough, a graph. And you go, oh, okay, let's look at a force and distance graph. So I exerted a force of 0.98 newtons over a distance of 2 meters. Okay, so here's my 2 meter mark. Here's 0.98 newtons. So, Ethan, could I find the area underneath this graph?
Yeah.
What would it represent? Yeah, because it's force times distance. So the area under a force distance graph gets you work, which is also equal to my change in energy. So in this case, what type of energy am I changing? Potential or kinetic? Potential. I'm changing my gravitational potential energy. So the area underneath a force distance graph gets you work. So obviously, if I exert that force over a longer distance, I lift it up higher, I'm going to do more work because I'm going to have a bigger area. If it's Hank, right, and I lift up Hank, well, that's going to take a lot more force to lift him up because he's heavier, so that's going to require a lot more work. Okay? So it's okay, well, that kind of makes sense. Now, here's the whole kicker to this problem, is that energy has to be conserved. So here's the basic idea on any of these problems. And these problems aren't difficult unless you try and shortcut this process and then it turns into a train wreck. So eventually we're going to have 4 different types of energy. We're going to have UG, which we've talked about, translational kinetic energy. So for now, these are going to be the 2 that we're going to deal with. Okay? We'll deal with the other ones later. But for now, these are the 2 that we're going to deal with. So we're going to have UG and kinetic energy. We can also have US, and that's going to be like energy stored in a spring. So like if I pull this down, I compress this spring, okay? I store potential energy, okay? And that gets changed into kinetic energy, okay? So I can have US, and I can also have rotational kinetic energy. So like when a bicycle wheel spins. So these are the 4 types of energy that we can have. For now, don't worry about these 2. We will later, okay? These will become important later on. They're just not anything that we're going to worry about for now. Now, so here's the basic idea. Just like momentum, the sum of the momentums before has to equal the sum of the momentums afterwards. The same thing is going to happen with energy. So this is going to equal UG prime plus KT prime plus US prime plus KR prime. Now again, don't worry about those. Well, you will, just not right now. So here's the basic idea, is that whatever energy that you have before has to equal all of the energies that exist afterwards. Okay, it's one of the great conservation laws that exist in all of science. Okay, now, here's the deal. You're going to work these problems, and trust me on this one, it makes life so much simpler. What you want to do is set up a chart. Okay, what type of energy can I have? In this situation, I can have UG, I can have KT, and then I can talk about the sum. So if there was a spring involved, I'd put a spring column. If I was talking about something spinning, I would put rotational in here. But for now, these are the only 2 that I'm going to worry about. Well, it'll be more complicated later on. This is just the beginnings. Okay? So here's the deal. If you set up these charts, it becomes so much easier. And I'm going to tell you right now, on the test, if I don't see this chart, I'm not even going to grade it. I'm just going to quit. Okay? So just get used to setting up the charts. They make life so much simpler. You're going to make so few mistakes because it's going to force you to keep track of everything that's happening. So here's the deal. So I've got Gary up here, 2 meters above the ground. What's the only type of energy that there is?
Potential.
Potential. Okay, I'm not throwing him, I'm not dropping, I'm just dropping. So this UG up here, this MGH, we said was 1.96 joules. So how much kinetic energy do I have? 0. So that means the sum is going to be 1.96 joules. So what that means, okay, and this is the significance of this. What this number means is the reality. That no matter what happens, everything in this system has to add up to 1.96 joules. Now, don't think, oh, this is 1.96 joules. That's like the universal energy constant. No. This is just 1.96 joules for this problem. If it was Hank, this number would be a lot bigger because the mass would be a lot bigger. Okay? But here's what's important, is that once you can isolate a system and find out one type of pure energy, whether that's a rocket sitting on a launch pad, Vanderbilt Air Force Base in California, and you're trying to get it to Mars, or you've got Gary sitting on top that I'm holding up here to a height of 2 meters. It's the exact same idea. Once you figure out what that constant is, then the only thing you can talk about is how you're going to change its form. So this becomes a constant. It's like, Shively walks in and he has $1.96. Okay, that's all he's got. He's got $1.96. Okay, he can give 96 cents to Magruto, says, hey, go buy Magruto, right? They're on sale. Hey, there you go. He's got $1 left over, gives that to Hunter. He says, hey, Hunter, go buy a Coke, whatever. Okay? So, but he's got $1.96 to give. That's all he has to give. He can change the location of his money, but that's it. So when you've got this, UG, 1.96 joules. That's what everything has to add up to. Now, the other way that you can visualize this is kind of like with a container. So you've got two containers. You have an UG container and you have a kinetic energy container. So initially, does your kinetic energy container have anything in it? Oh, it's bone dry, it's not moving, right? So this is going to be 1.96 joules. So as soon as I let go of it, okay, as soon as I let go of it, what happens to that kinetic energy?
It's just getting bigger.
Starts getting bigger. Why? It's accelerating, so it's going faster, right? What's happening to the amount of UG?
Smaller.
Smaller. Why? Because what's getting smaller?
Height.
Height. So I'm transferring UG into kinetic energy. This H is getting smaller, my kinetic energy is getting bigger because it's going faster. Okay? So imagine that you have like a siphon that connects these two containers. So as soon as I let go of it, it starts to siphon this energy from here over to here. Now, how do I know that I had to do work to get this thing up here? If I'm sitting here and that is right there in the tray, why do I not have to worry about in the middle of a lecture this thing starting to lift up on its own? Why is it not going to happen?
Zero.
Well, Mother Nature just says screw it.
Lazy.
Yeah, it's lazy. Mother Nature goes, you want that thing up there, you lift it up there. Because you're going to store potential energy. So this is where this idea of work and potential energy and kinetic energy all become intertwined. So I've got to do a certain amount of work to lift this thing up here. Because if I'm in the middle of a lecture and I look over and I see this thing starting to go up on its own and then begin to hover, it's like, especially coming out of surgery, it was like, okay, time to get off the painkillers. Okay, this is bad. But it's not going to happen because of the fact that Mother Nature's lazy. It's like Mother Nature's going, hey, I'm kind of gelled out here in the tray. I'm not going to go up there. Okay, if you want it, you've got to lift it up there. But once I store that much energy, then everything has to remain the same. So, at the point where it just hits the ground, Fonda, at the point that it just hits the ground, here we are at the bottom, okay? How much UG do you think I'm going to have?
Yeah,
Why?
because it's all kinetic.
Beautiful. So I don't have any UG, okay? Because my height has gone to 0. Okay, it started off at 2 meters and now it's gone to 0. So if this is 0, how much kinetic energy do I have, Vonda?
1.96.
Beautiful. I got 1.96 joules. So then, guess what? The sum still has to add up to
1.96.
1.96 joules. Okay? Now, here's what's important. Is kinetic energy a vector quantity or a scalar quantity? Scalar quantity, right? Doesn't have a direction. So this goes back to the assignment that I just gave back, and it was a question about Hank and Hank swinging down versus Hank being dropped. And some of you were saying that, and I want to clear up this misconception that you all kind of have right now versus Hank is just dropping straight down. So some of you were saying, oh, it's the same because it's the same force and it's the same acceleration. No, 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 no. Okay, no. If something swings down on a pendulum versus something is dropping straight down, the accelerations are vastly different. Okay? The acceleration on the pendulum is vastly different than something just falling straight down. Okay? Straight down is when you get your maximum acceleration. Or the other way you could look at it is if you had it like moving down a frictionless inclined plane. So here's what you want to look at when you have like something that's being held up and then changing into kinetic energy. The path that you take doesn't make any difference in terms of the energy transformation. It's just like, you know, I said, hey, Bree, what'd you do? She goes, hey, I went to Chicago over break. Okay, cool. How'd you go? She goes, well, I flew from here to St. Louis and then got a train from St. Louis to Chicago. Okay, hey, that's nice, okay, right? I said, Mary, what'd you do? I said, oh, Mary goes, hey, I went to Chicago too. Okay, Mary, how'd you go? Well, I drove to Kansas City and then I got on a camel and rode a camel from Kansas City to Chicago. Okay? Now, do they both end up in Chicago? Yes. How they got there is vastly different. But the overall change in their location is the same. They both were from Wichita. They both went to Kansas City, to Chicago. Okay? So the net change is the same. The timing is completely different, but they both end up in Chicago. So the same thing is going to be true. If I let something swing down or just drop straight down or roll down an incline, as long as the heights are the same, they do end up with the same kinetic energy. But the accelerations are completely different, the times are completely different. But what is common is the idea that energy is conserved. The accelerations are completely different, especially if you let something roll down an inclined plane. That acceleration is going to be really, really slow as opposed to just dropping something. But the overriding theme is exactly what Vonda had said, is that once you get down to the bottom, you don't have any kinetic energy. How you get to the bottom doesn't matter. How you get to Chicago doesn't matter, as long as you get to Chicago. Okay? Fly, plane, train, camel, whatever. Okay? You're just going to get to Chicago. Net transformation is the same. So, how could I use that number, the fact that it has 1.96 joules of energy, how could I use that to figure out how fast it's going? Tori, how could I know that, here's my kinetic energy, how could I use that to find how fast it's moving?
I don't know.
How do you calculate kinetic energy, Tori? Let me give you a hint. It starts with 1/2.
1/2 mv squared.
Beautiful. Do you know the mass of the ball?
Yes.
Do you know what 1/2 is?
Yes.
You know the kinetic energy?
Yes.
Can you find the velocity?
Yes.
Okay. So, kinetic energy is 1/2 mv squared. True? So, Tori, how am I going to get V by itself?
It'll be 2k
Yep.
divided by m
Yep.
square root.
Beautiful. So, the mass is going to be 2 times my kinetic energy divided by, my velocity, divided by my mass. So in this case, somebody take 2 times 1.96 joules and divide that by 0.1 kilograms. Should be 6 something.
6.26.
6 point what?
26.
6.26 meters per second. Okay? It's kind of cool, right? 6.26, boom, here we go, we're off to the races. Now, temporarily, I want you to forget all about this number. Okay, I want you to pretend that this doesn't even exist. We have never talked about this before. You know nothing about energy. Okay, you know nothing about this. Now, pretend that you were getting ready for your acceleration test, let's say, way back, like 4 equations. It's like, oh, physics is so pure and something like that. And I say, all right, class, here's Gary the golf ball. I'm going to drop Gary. Gary's going to fall for 2 meters. I want to know how fast Gary is going when Gary hits the ground. Now, back when we did acceleration, did I ever give you the mass of Gary the golf ball? No. No, you know why?
Doesn't matter.
Didn't matter. Didn't matter. You didn't know anything about forces. You didn't know anything about gravitational fields. You didn't know anything about energy, momentum, nothing. Okay? Life was simple back then, right? So, if I gave you this problem and said, how fast is it going when it hits the ground, what would you use? You'd use that equation. Oh, yeah, right? V squared equals V naught squared plus 2AV. What's your initial velocity?
0.
0. It's a big goose egg, right? So in this case, we're going to take 2 times 9.8 meters per second squared times the height of 2 meters. So somebody run the numbers, and I guarantee you, you're going to get 6.26 meters per second. Now, here's what's important. You can't have one branch of physics, the guys that do, oh, here's the kinesiology, or the kinetics equations, okay? And they're saying, oh, you're going to get 6.26, okay? And then you've got another group of physicists, okay, that are going, whoa, 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 we're the energy people. We get an answer of 8 meters per second for the exact same situation. You can't have one group of physicists saying, oh, the velocity is 6.26 meters per second, and another branch of physics going, no, it's about 8. No, okay, one of you is wrong, okay, one of you is horribly wrong, right? And so that's the beauty of this. So when we work this from an energy perspective, all I'm doing is giving you like a different way to view this problem. So, okay, this was old school, right? And y'all could do this, and it's cool. And I never gave you the math because it didn't matter. But this, you're going to get the exact same answer, but now you're just viewing it from an energy perspective and go, oh, now I know where that comes from because energy has to be conserved. Okay. Now, I got one more problem to do with this. So here's the Gary the golf ball. Still starting from 2 meters above the ground. And he's going to fall. And I want to look at what happens when he crosses the 1 meter mark. So when Gary crosses that 1 meter mark, about yay, okay, I want to know how much UG he's got. I want to know how much kinetic energy he's got. And I want to know how fast he's moving. So when he starts up here, so when he crosses this 1 meter mark, I want to know UG, kinetic energy, and the velocity. Now, here's the basic idea. When he crosses that 1 meter mark, what are the two types of energy that he's going to have?
Kinetic and potential.
Potential and kinetic. So he's going to have some UG, and he's going to have some kinetic, and he's going to have the sum. So this is when he crosses the 1 meter mark. So what's the sum of all that energy still have to be?
1.96.
1.96 joules, because that's what brought us to the dance. That's how much work that we did to store the energy. That's what we've got. So this is going to be 1.96 joules. So of these three numbers, what's going to be the easiest to calculate? Of those three.
UG.
UG. UG's going to be the easiest. What do you have to have UG?
Height.
MGH, right? Simple. That's the easiest one to calculate. So my UG then is going to be MGH, which is going to be that mass of 0.1 kilograms times G times the height of 1 meter. Now, here's what I want you to be careful of. This H is how far it is above the ground. It's not how far it's fallen. Okay? It's how far it is above the ground. So if you look at that calculation of the InSight when it was approaching the surface of Mars, the H that we used wasn't how far it was from the Earth. Okay? The H was how far it was above the surface of Mars. So when you're doing this, it's not how far it's fallen. It's how high it is above the ground, which in this case is the same number. But anyway, you do the numbers, you get 0.98 joules. So how much kinetic energy do you have to have then? 0.98. So basically we've split it up. Okay? So that way everything still adds up to 1.96 joules. Now, here's the question. Does your calculation of UG change because it's moving when it crosses the 1 meter mark? No, because what's the only thing that you have to calculate UG?
Height.
MGH, that's it. The fact that it's moving doesn't make any difference, okay? The fact that it's orange doesn't make any difference, okay? The only thing you have is how high it is above the ground. That's the only thing that you have to know. Okay, so we got that. Now, let's talk about the velocity. So, here it is. It's 2 meters above the ground, crosses the 1 meter mark. When it lands, it was going 6.26 meters per second. Okay? Now, oh, God, don't sneeze after surgery. Whoa. Oh. Okay.
Stains in the white shirt.
Thanks. Blend in with the JPL thing. That's why I wore a red tie, so it's kind of color coordinated. Okay. So when it crosses the 1 meter mark, at that point we have half potential and we have half kinetic, right? So this is 0.9 and 0.98. So here's the question. Then does it seem reasonable, since we've converted half of it into kinetic energy, and it lands at 6.26 meters per second, does it seem reasonable then that the velocity would be half of that and would be 3.13 meters per second? So that's an option. It's okay, we've lost half our energy as potential, it's into kinetics. It lands at 6.26, half of that would be 3.13. Okay? It's an argument. I'm not saying it's a good one. I'm just saying it's an argument you can make. Now, the other one that you could do is you could sit here and go, well, I got kinetic energy is v squared, so when you square something, that makes it, bigger. So maybe the velocity at that point is going to be less than 3.13 meters per second. Like it might be around 3 or something like that, because it's going to get squared and that'll make up the difference. Okay? Or you can make the argument that, well, because it's squared and it's going to fall, right? And that gets squared, maybe that's going to be greater than 3.13 meters per second, maybe around 4 or something like that. Okay? So these are your options. When it crosses that 1 meter mark, it could be less than 3.13. It could be equal to 3.13, which is exactly half, or it's going to be faster than 3.13 meters per second. What's your gut feeling?
1.
Less.
Less?
Bigger.
So how many vote less? Okay? 1, 2, 3,
I feel
4,
like I don't want to go.
6, 7, 8, 9. Mary?
What?
Are you voting that way?
No.
Okay.
Wait,
10. McGriddle?
is Mary voting?
Yes, I am.
11.
Is Mary voting?
12. Madeline?
Yeah.
12. 13. Okay? So we got about 13 people on the less than train. What about just exactly equal? Because we split the energies and it's going to be half the velocity.
Don't do it, anyone. Okay.
No one's on the...
Don't.
You already voted. Okay, no one's on the half train. Okay? What about the greater than train?
Mary's
1,
voting.
2, 3, 4, 5.
I'm going there.
Okay, 5. Okay? So why did you all vote less than? Let's talk about the group that voted less than. Why did you vote less than?
Because it's being squared. Gravity is accelerating.
Yeah,
So-
gravity is accelerating.
I mean, okay, the ball is accelerating, right?
Yes?
So it's not going to be exactly equal, but it's not going to. There's no way it could be greater, because then that would mean that it's going to slow down.
Yeah,
But
Okay.
it's speeding
like
up.
as it falls, it's gonna get faster and faster.
Okay.
Yeah,
All right. Okay, I like that. And it's squared, so
it's squared.
okay.
The math works out.
Math works out.
Yeah.
Okay.
Why you're going.
So Mary, you're on the greater than train.
Yeah.
Why?
Because before you asked the question, I calculated it.
Yeah.
That's cheating.
That's cheating.
No, you can.
If you hadn't calculated it, Mary, what would you have chosen?
Probably the less than.
Probably the less than. Okay. Now, before we get to do the calculations, okay, pretend that you haven't done the calculations, okay? Great mentioned acceleration due to gravity. Okay, what's the acceleration caused by gravity on this rock that we're on?
Oh my God. 0 meters.
9.80 meters per second, right? So this changes linearly as a function of time, right?
Yeah,
Okay?
you're done.
It changes as a linear function of time. So for every second that goes by, this is how much it changes. True?
True.
Now, notice this is not 9.8 meters per second per meter, okay? Where it changes so much for every meter that it falls. it changes so much for every second that it falls. Okay? Now, again, before you touch a calculator, here's what I want you to think about. When is it going to be in the air longer? When it falls the first meter, or when it falls the second meter?
First meter.
First.
Why?
Slow.
Because it's stopped.
Starting off slow, right?
Nice
Yeah.
and easy.
Right?
Yeah.
And
Hey,
then
but 13 other people.
this is going to take less time for it to fall, right?
She cheated.
Okay? I want you all to keep this in mind.
You can cheat.
So Mary. Mary.
Slide control.
So you actually calculated the velocity, right? So you took 2 times, and you used the Torrey equation, and I'm guessing you took 2 times 0.98 joules, divided that by the mass of 0.1 kilograms, and took the square root of all of that, and you got what?
4.43 meters per second.
4.43 meters per second. Okay? Which is solidly above 3.13. Okay? Solidly above that. Solid. Right? And here's the reason why it's that. It's because that velocity, when it crosses that point, is going to change more in the first meter than it is in the second meter, because it's going to take more time to follow the first meter than it is going to take to follow the second meter. Okay? So that's why the number is so much bigger. Makes sense? Okay. All right. Cool with that? All right. So no worries there. So stop that for a second. And I highly recommend like Mexican four cheese. Yeah.
Yes, sir.
Kick to it. I've done it with like jalapeno cheese. That's a bit for my.
I use sharp, so it's like it wasn't bad.
What?
Do you eat pizza like any kind of pizza? You know? Do you eat the crust?
Occasionally, not on a regular basis. What?
He
You
likes
make it
pizza
sound like I'm a
bones.
horrible person.
If it's good crust, you need. Sometimes the crust just isn't
No,
good.
just eat the crust. It's not bones.
I mean, if it's
It's
not.
food.
No, bones is.
Well, that's some pretty tasty bones.
If it's not good, why would you eat it?
Okay.
I don't
Anyway.
eat little pieces of crust. That's the only thing.
Come on, man. Just eat the crust.
Anyway,
It's not gonna kill you.
how did this come up in conversation?
Because
Well,
at lunch,
at
Garrett
lunch,
didn't eat his crust.
Garrett didn't eat his crust. Landon didn't eat his crust. Like
so
we're in
Matt called them
kindergarten.
children.
If it's
Like we're
not
in
good, I'm not gonna
kindergarten.
eat it.
It's called
Why
crust.
subject myself
It's
to it?
crusty.
Just eat it.
Okay, anyway.
It's not bones. It's not.
Okay, now, let's reverse the process. So what if I take Gary the golf ball and I just throw him straight up in the air? So now it's just the reverse. It's the same idea, but it's just the reverse. So if I throw him up in the air, the very split second that it leaves my hand, what's the only type of energy that it has?
Kinetic.
Kinetic energy, okay? So if he's going to 20 meters per second, that kinetic energy is going to be 1/2 the mass of 0.1 kilograms times 20 meters per second squared. So somebody take square 20 and then take a half. Should be, I think, 20 actually. Should be weird. 200? No.
One, hold on. Yeah, it's 20.
It's 20.
Yeah.
Okay, that's cool. So here, but it's the same idea, but just a little bit different. So now, once I launch him straight up, like this, okay, that kinetic energy is going to be 20 joules. So how much UG does it have at the very beginning?
0.
0. I don't have any here, right? So this is just going to be 20 joules. That's it. There you go, 20 joules. Now, as it goes up, what's going to happen to your amount of kinetic energy? It's going to decrease. What's going to happen to your UG? It increases. So this is at launch. So up at the very top, how much kinetic energy does it have? 0. Why? It's not moving because you're going to change direction, right? So once you change direction, your velocity has to go to 0. Okay, so I don't have any kinetic energy here. That's 0. So then my UG is going to be 20 joules. So now, how could I use this UG to find the maximum height?
Well, you know that UG is equal to mgh.
Yeah, that equals mgh. Boom, you're off to the races. You can find the height that way. So if you launch something up in the air, it's the exact same idea. Okay? You're going to start off, you're going to have all kinetic. At the top, it's going to all change into potential. And then when then it falls back down, all of that potential is going to change back into kinetic. Okay? It's the same idea. Whether you launch it, whether you drop it, it doesn't make any difference. Now, let's make things a little bit more complicated. Okay? Just a little bit. So, instead of just like dropping Gary, I'm going to throw Gary down. Okay? So I'm here, instead of just doing like this, okay, having a bit of a bad day, okay, I'm going to throw him down. So when I throw him down, now what type of energy does he have at the beginning?
Potential and kinetic.
Kinetic and
Potential.
potential. So when I throw him down, okay, when I throw this down, now what I'm introducing is some kinetic energy, but does he still have the same UG?
Yeah.
Yes, because the UG isn't dependent upon him being thrown, because the UG is just dependent upon mgh. So it's going to have some kinetic energy and it's going to have some UG. So if you look at this from like a chart perspective, okay, you've got UG, which is going to be mgh. You got some kinetic energy, which is going to be 1/2 m. Now, I'm going to use v naught squared, because that's going to be the initial velocity that I have when I throw Gary down. So that's going to be some v naught value. I'm going to throw it down. Now, that has to equal the sum. I don't know what these numbers are. I don't know, and I don't care what they are. All I know is that they're going to be some number. So if that's the case, this sum here is going to be mgh plus 1/2 m v naught squared. So that's going to be the total amount of energy that I'm going to have. Now here's an interesting idea. When it lands, this is when I throw it, when it lands, how much UG do I have?
Good.
0. Don't make this difficult. That's still going to go to 0. But is now what happens to all of that energy? Now all of that energy is in the form of kinetic energy. Now, that's going to be 1/2 mv squared. So guess what? When I add this column together, what does that have to equal? Whatever I started with over on the left-hand side. So this has to equal 1/2 mv squared. So here's my final velocity, there's my initial velocity, and that's going to be mgh. Now this is the cool thing about this. If I just drop Gary, what happens to this part?
It
Goes away.
It goes away. So then basically UG equals your kinetic energy. But here's an interesting idea. This is if I throw Gary down like this. Now, instead of throwing Gary down, what if I throw Gary up in the air? If I throw Gary up in the air versus throwing Gary down, is that going to change that V naught calculation?
No,
No.
it's still 0.
Well, no. Well, it's still going to be the same value.
Yeah.
Because remember, kinetic energy is a scalar quantity. Okay, which direction I throw him doesn't make any difference. So when I look at this number, whether I throw Gary up in the air or I throw Gary down, it doesn't make any difference. As long as I throw him with the same velocity, it's still going to have the same amount of kinetic energy. Now, you okay, Fawn?
Yeah.
Now, would the same calculation be true if I threw Gary at a 45-degree angle? If I threw Gary like that,
Yeah.
still be the exact same thing, because it's still the same velocity. It doesn't make any difference which direction that I throw it. It's still going to end up being the same thing, because it's a scalar quantity, because it doesn't have a direction. Okay? Got that? Okay, so stop that. Question number 4. Okay, about the archer pulling back. So here's the reason that I told you it was an average force. Because you can model that like me pulling down on this spring. So the initial, when I pull it down initially, it doesn't take very much force. But the farther that you pull it, the harder it is to compress it. So this is why I'm telling you on this one, what's happening on this problem is that you're pulling this bow back like this. So on average, you're going to exert 201 newtons of force. Okay, so just use that as the value for your force, and you know how far you pull it back. Do not make this difficult. You're going to draw a force distance graph. You're going to have 201 newtons over that distance. It's a rectangle. Don't make it difficult. Now, so when I pull this back, do I do work?
Yes.
I'm storing potential energy, right? So when I let go of it, what's going to happen to all of that potential energy?
It's going to release this
It
connection.
changes into, oh,
Broken light.
that too.
Oh,
How many people have
getting
stopped?
everybody.
Oh my goodness.
Okay, okay.
Just got him a second time.
All right. So, here's the deal. So, however much potential energy I store is how much kinetic energy it's going to have when it's launched, which is going to be the same amount of when it succeeded. I'm going to store potential energy in the spring. That's going to turn into kinetic energy when it's launched, and that kinetic energy is going to equal the
Potential energy.
potential energy at the top. Okay, so all you're doing is just going through a transformation of that. When you get to question number 5, keep this example in mind. Okay, keep this example in mind. You're going to throw something. You're going to have potential and kinetic energy at the top. Set that equal to the kinetic energy at the bottom. You've got to keep track of 2 different velocities, a v naught and a v. When you get to question number 8, do not make number 8 difficult, okay? I've given you the net upward force of 3.89 times 10 to the 3rd newtons. That's the number that you use in your calculations. You don't have to subtract out the weight of the ship. I've already done that for you, okay? So on number 8, do not make it difficult. That's your force calculation that you're going to use in terms of force times distance equals your work, which is going to be your change and everything else. Okay? Do not make that difficult. Okay? All right, I'm done. You're on your own. Let's see if we can figure out what's happening with NASA.